All right, today we are going to be talking about vectors, which those of you who have taken physics or multiple physics courses are probably pretty familiar with these. I have heard in the past, although the last couple times I've taught this course, I haven't had any issues, but if you've learned to do something differently from physics or whatever, it's always okay as long as you're showing your work and you're getting the same answer. So if you've learned a different method in the past and it's working for you, that's certainly fine for you to continue using. So when we are talking about vectors, we have to understand that a vector quantity, which we are going to symbolize like these. You can see it's got like, this is what it looks like if you draw it yourself. That's the symbol for vector. So this would be red vector V. When we have a vector quantity, unlike just a scalar quantity, a vector itself is composed of two different measurements. It's magnitude and its direction. So when we're talking about magnitude and direction, we have to think about what those are actually meaning. The magnitude is typically, if we're talking about a real life situation, the magnitude is often like a weight. Sometimes it's also a length. When we're just drawing a vector, we'd be talking about the length. Like I said, in a real life situation, often the magnitude is a weight or a force. But when we're talking about just drawing one, that would be the length, and we use the distance formula if we're trying to find length in a coordinate plane. So you can always use the distance formula to find the magnitude. The direction of a vector, that's going to be described by the angle. So when we are talking about a vector, the standard position vector has its initial point at the origin. So that means that the vector starts at 0, 0 and goes to AB. And again, that's not only going to have a length from 0, 0 to AB, but it's also going to have an angle. So when we are talking about this type of situation, our vector itself, so again, we'll just call it vector V. That's generally what we use for a general vector. If we're going from 0, 0 to AB, that's going to be A vector I plus B vector J. I and J are what we typically use for a unit vector. So this is kind of like the standard form, kind of like A plus BI is standard form in complex numbers. This is going to be standard form for our vectors. When we are trying to find the magnitude symbol looks like kind of a double absolute value. And just so you know, in your book, they explain, if you read through the section, that when you bolden a letter, that also can mean vector. So sometimes they don't use the symbol and they just make, the letter V bold, and that's supposed to indicate the same thing. Obviously, we don't bold on our own, so you do need to, in your homework, on the quiz, on the final exam, anytime you intend for something to be a vector, you do need to put the symbol above it. So this we would read the magnitude of vector V, and because magnitude is going to be length in this case, the distance formula in this case, because it'd be x sub 2 minus x sub 1 squared, and then the same thing with B, we actually, because this is 0, 0, end up with the square root of a squared plus b squared. So this same formula that we used in 6.5, we are going to use again here, but to represent the magnitude. So magnitude is this guy right here. Two vectors, we call them equal if they have the same magnitude and the same direction. So meaning that they've got the same angle of rotation to get to where they're going and they're the same length. When we are talking about vectors, we can add and subtract vectors. We're going to do that today. You can also multiply a vector by a scalar, meaning you could just take 2 times vector v, or 1/2 of vector v. We don't multiply vectors by each other, so to speak. In section 6-7, we'll deal with something that's similar to vector multiplication, but really we're just multiplying by scalars in this section. We do those 3 things, the addition, subtraction, and multiplying by scalars, the same way as we would with real numbers and variables. So nothing that seems strange on that. When we are converting to standard position, our vector v is going to be equal to whatever your 2x coordinates are subtracted, and that'll have a vector I next to it because that's the unit vector for our first position. And then for y, we would do the same thing, y2 minus y1, and then multiplied times vector j. So that converts us to standard position. We have our unit vector I that is going to be along the positive x-axis. J is along the positive y-axis. So hence y, we have this connected to the I because it's x, and this connected to j because it goes with the y. Sometimes we're going to be asked to convert a vector that we have to a unit vector that has the same direction as our original vector. When we do that, what we need to do is take the vector itself, so vector v in this case, and of course if we change this then it would match. So if we were talking about vector w would be in the numerator, and then we divide by the magnitude of that original vector. And that will give us a unit vector that has the same direction as our original. We also need to know how to convert to IJ form, which is like polar form looking. So we have vector v would be the magnitude of vector v times cosine of theta times vector, oops, that's not supposed to be a j, and I don't have an eraser tool, that should be an I, sorry, plus magnitude vector v times sine theta vector j. So this, if it says convert it to IJ form, this is what we're going to do. So you would need the magnitude, you would need the angle in order to do that. It's also important to know that we can use the same formula to break things down. So sometimes I might be looking for the actual theta. And if I'm looking for theta, then I know that the cosine of theta is going to equal whatever my A value is, because typically we would have A cosine theta. It's going to be your A value divided by, because we'd be getting rid of this magnitude. So A divided by the magnitude of the vector. We also know, likewise, that the sine of theta would be equal to B divided by the magnitude of the vector. So if you need to find the angle, these are 2 different ways that you could do so. Okay, so that gives us our background information. Again, like I said in 6.5, most of the formulas from these sections are not on the typed part of the formula sheet for the final exam, which means that you probably want to make sure that everything from these sections goes in your box, unless you want to memorize it. All right, example 1. Sketch vector v equals 5 vector I minus 3 vector j and find its magnitude. So vector I, remember, is along the positive x-axis and vector j would be on the y-axis. So in this case, because vector I is multiplied by a scalar of 5, that means that we're going to go 5 to the right. Here, vector j is multiplied by a scalar of -3, so that means we're going to go right 5, down 3. This is the point we're going to go through, 5, -3. And our vector itself is, it's so hard to draw lines. Curves are a lot easier, so sorry. It just will kind of look like a little ray that starts at the origin and goes through 5, -3. So that would be our sketch of our vector. So then we also have to find its magnitude. So magnitude of vector v is going to be the square root of a squared plus b squared. A is 5, b is -3. So that gives us 25 plus 9, which is 34. And square root of 34 does not simplify. So that means that that is going to be our final answer for our magnitude. So magnitude, sketch, and we're done. Example 2, a pilot flies due south with an airspeed of 192 miles per hour. A wind from a direction of 78 degrees is blowing at 23 miles per hour. Draw the vectors and the resultant. So resultant means the sum. So here, resultant is going to be what we get when we find the sum of those two vectors. So first, we have to sketch them. So I'm going to change all my colors here. So I'm going to draw my axes first. And then let's do my first vector in blue. So it says it flies due south with an airspeed of 192. So due south means I'm starting at 0, 0, and I'm going straight down. So again, hard for me to draw lines, but in blue, this is my vector. The speed we use as the magnitude because it's, kind of like a force. So 192 miles per hour. So I'm just going to label this 192. And really the direction that I would be going here, it doesn't say, but I know that in order to get from 0 to here, that's going to be 270 degrees. So that is my theta that goes with a due south vector. All right, now I'm going to go, let's use like a fuchsia maybe here. Maybe green would show up better. Okay, the second one, we have a wind from a direction of 78 degrees is blowing at 23 miles per hour. So 78 degrees, maybe to about here. And draw in the vector going from the origin. And again, its speed is 23, so that becomes its magnitude. Okay, if I want to find the resultant, that means that I need to add the vectors together. Well, right now, all I have is the sketch. I need to actually write them in my I plus j form before I can ever find the sum. So if I switch back to my blue, we'll call that maybe vector v for our first one. And if we look up here, we know that our ij form should look like this. And in order to add things, I really need the vectors in this form. So it's going to be the magnitude of the vector, cosine of the angle, and then vector I. Then magnitude of the vector, sine of the angle with vector j. So in this case, my magnitude, which was the speed, so that's 192, and then I'm going to do cosine of 270 degrees, vector I, plus magnitude sine of 270 degrees, vector j. Now, of course, I need to simplify these. Cosine at 270, the ordered pair there is 0, -1. So the cosine is 0. So I've got 192 times 0 times vector I, which is just 0. Then the sine at 270 is -1. So I've got 192 times -1 times vector j. So that'd be -192 vector j. 0 minus anything, of course, just gives us -192 vector j. So this would be our I plus j format of my first vector that they described. Now, I go back and do the other, so let's call it vector w maybe. We had 23 as our speed, so that's our magnitude. Then we're going to do cosine of 78 degrees vector I plus, same thing, but with the sine of 78 degrees and vector j. And so obviously this isn't a unit circle value, so I can't do that. So I am going to have to go to my calculator. It is okay, obviously, to use decimals because it's not a unit circle value. So clear that off and make sure I'm in degree mode. Yes, I am. So we're going to do cosine of 78 degrees. And then we will also need the sine of 78 degrees. And so I have 0.208 and 0.978 approximately. So I've got 23 times 0.208 vector I, and then 23, already forgot what it was, 0.978 vector j. And then I need to simplify those. So I'm going to take this guy up here. I'm not going to take the rounded value. I'm going to take the actual value and multiply that by 23 just so I can get these accurate. I think that they typically tell you to round values to the nearest hundredth. So we want to round at this point, not at this point. It's okay to write it down on your paper in rounded value, but in your calculator, use as many decimal places as you can. So 4.78 is what we get there. So I have 4.78 vector I, and then for vector j, we take the 0.978, the whole thing, times the 23. That gives us 22.50. So I'll just write 22.5 vector j. So these are my individual vectors in my unit vector form, the I plus j form, which is the form that I need in order to find the resultant. So when I add and subtract vectors, I do that just as if they were variables. So it's really just like combining like terms. So if I want to take these to find that resultant, I'm just doing these two things and adding them together. So the -192 vector j is a like term with the 22.5 vector j. So all I'm really then going to do is take the 22.5 and subtract 192 in order to get that resultant. So minus 192, and that gives me negative 169.5. So that's going to be the coefficient of vector j. Obviously, the vector I here didn't have anything to combine with, so it's going to stay the same. So 4.78 vector I, and then minus 169.5 vector j. And that becomes my final answer. All right, this one wants me to write in terms of I and j, but this time, instead of being given magnitudes and directions, I'm given just 2 points. So in this case, I'm just going to use the formula that I have up here. Converting to my standard position, if I have the points, I'm just going to take x2 minus x1, make that the coefficient of I, y2 minus y1, and make that the coefficient of j. So in this case, I'm going to say vector v equals x2, which would be 7, minus negative 4, minus negative becomes a plus. And then I have negative 6 minus 3 to go with my vector j. So that gives me 11 vector I minus 9 vector j. So a lot easier when I just have the 2 points. Now, of course, example 2 was more complicated because I also had to find the resultant. So example 4, here I showed you what it might look like if they choose to just use the boldened versions rather than using the symbols. But it means the same thing. So this is 2 vector u minus 5 vector v. So this has really three different operations within it, because I have scalar multiplication on both of the vectors, and then I have subtraction. So I'm just going to write it out. 2 vector u, which is 3 vector I minus 6 vector j, and then minus 5 times vector v, which is negative 4 vector I plus 8 vector j. So now I'm going to distribute, because multiplying by a scalar, we treat it just like we would with real number properties. So that gives us 6 vector I minus 12 vector j. And then over here, I have positive 20 vector I minus 40 vector j. So like terms here, like terms here, and we're just going to combine them. So 26 vector I minus 52 vector j. And we're all done. All right, on B, this one asks me to do subtraction of the 2 vectors, and then it wants the magnitude. So the order does matter. I do need to do the subtraction inside the magnitude first. So if I have vector w is first, so negative 2 vector I minus 6 vector j, and I'm subtracting vector u, which is 3 vector I minus 6 vector j. Remember that when I'm subtracting, I have to distribute my negative. So I have negative 2 vector I minus 3 vector I, which is negative 5 vector I. I have negative 6 vector j, and then minus negative becomes a plus. So I have negative 6 vector j plus 6 vector j, which is 0 vector j. Now, you don't have to write 0 vector j. I'm just writing that to illustrate, because this would just be negative 5 vector I. But when I go to find the magnitude, remember that the formula is usually the square root of a squared plus b squared. In this case, b is 0. So again, you don't have to write this if you don't want. That is going to give us 5 for our magnitude. All right, on to the back. Example 5, find the unit vector with the same direction as vector v. So In order to look at this one, we have to use this formula up here. Sorry for the scrolling. Unit vector with the same direction as vector v. So that would be this guy right here. So I'm going to find its magnitude first. So the magnitude of vector v in this case is the square root of 3 squared plus negative 4 squared. So 9 plus 16, which is 25. So that's going to give us 5. So I'm going to take vector v itself, because again, this is the formula we're using. And so I do 3 vector I minus 4 vector j. And I'm just simply going to divide it by 5. Now we do want it in unit vector form. Unit vector form is the vector I part first, the vector j part second. So just separate the pieces. 3/5 vector I minus 4/5 vector j. So it sounds really complicated, but the math that goes with it is pretty easy. Okay. Example 6, write the vector with magnitude equal to 6 and theta equal to 30 in terms of I and j. So this one, we really kind of already did this when we did the resultant vector in example 2, but this is just a simplified version. So if I want to write it in I plus j form, my vector is going to equal magnitude, which is 6, times the cosine of the angle, vector I, plus magnitude sine of the angle, vector j. And so simplifying, notice that when we did the word problem, I told you to use the calculator on this one because it was not a unit circle value, but here I used the unit circle. 30 degrees is a unit circle value, so you really should use fractions and radicals on this one, and not be pressing it into your calculator. They will expect an exact answer here. So at our 30 degrees, we know that our cosine is radical 3 over 2. So I've got 6 times radical 3 over 2, and then that's going to be with my vector I. The sine of 30 degrees is 1/2. So I've got 6 times 1/2 times my vector j. And then I'm just going to simplify. So here I get 3 radical 3 vector I plus 3 vector j. And we don't treat the vectors like we would imaginaries. We're not going to put the vector in between or anything. It should go after. And that gives us our final answer. All right, last one. The magnitude and direction of two forces acting on an object are 250 pounds north 60 degrees east and 150 pounds south 45 degrees east, respectively. Find the magnitude of the resultant force to the nearest pound and direction angle to the nearest tenth of a degree. So this one, similarly to example 2, is going to have a lot of steps because we've got two different vectors that we're talking about, two different forces, and we have to find the resultant force. So again, resultant force is when we're going to add them together. So resultant force is going to be the sum. So since it says these are two different forces, I'm going to call my two vectors this time vector F1. So force 1, if you will. I am going to draw a sketch because I think it will really help you because we have bearings here. And so often when we have these bearings, people mistakenly just take the angles and make those the thetas. And that is not the case when we have a bearing, because remember that your theta is a measurement from 0, being an angle in steady standard position, whereas a bearing is not. So if I actually draw out north 60 degrees east, and we'll use that blue here. So I'm heading north and I'm turning 60 degrees to the east. If this is 60 degrees, that means that this is 30 degrees. And 30 degrees is going to be my theta 1, because that is the amount that I'm actually traveling to get there. So in this case, the weight, I have 250, so that's the magnitude of the force. So magnitude, then I'm going to have cosine 30 degrees, vector I, plus magnitude sine 30 degrees, vector J. And even though 30 degrees is a unit circle value, we will probably just use the decimal versions because this is a real life situation and it wants us to round to the nearest tenth and nearest pound anyway. So in order to save myself time, I'm not going to use the calculator here, especially since I have it right above. I know this is radical 3 over 2, and this here is going to be 1/2. So I don't have to press it all into the calculator, but I am going to want a decimal version on this 250 times radical 3 over 2. So pull up the calculator for that part at least. So 250, and then I've got radical 3, and then dividing that result by 2. So I get 216.51 approximately. So 216.51 vector I. My vector J is going to come out nicely because it's just 1/2, so I don't need the calculator for that. So this is my vector F1. Now I'm going to find vector F2. So vector F2, it says it's 150 pounds, so that's its magnitude. Now I'm going to draw out south 45 degrees east. So heading south, turning 45 degrees to the east. So that would be right here. Now again, this is the bearing from here to here. But what I actually need is the theta. And the theta is going to be this angle right here because it's from 0. So that theta 2, this was 45 degrees, so I've got 270 plus 45, so that gives me 315 degrees as my theta 2. So I've got cosine of 315 degrees, vector I, and then 150 sine 315 degrees, vector J. This is a unit circle value. So I do know in quadrant 4 that cosine is positive and it's a 45 degree reference angle. So radical 2 over 2 for this guy. And the sine, same idea, except it's going to be negative. So negative radical 2 over 2 vector J. So in my calculator, I'm going to need to do 150 times radical 2 over 2. So I know that half of 150 is 75. So really 75 radical 2 is what I need to know. So 75 radical 2, which gives me 106.07. And they're both the same here. So 106.07 vector I, and then since this one was negative, it'll be minus 106.07 vector J. So the resultant force, so we'll just use plain F for the resultant, is going to be what we get by taking F1 plus F2. So again, all we're going to be doing is combining like terms. So these guys are like terms, and these guys are like terms. So I do the 216.51 plus 106.07, which gives me 322.58 vector I. And then 125 minus 106.07 gives me 18.93 vector J. So this is the resulting vector, but what it asks us to find is the magnitude of that resultant force and its direction angle. So in this case, our magnitude we would get, so magnitude vector F is going to be the square root of 322.58 squared plus 18.93 squared. So square root 322.2, oops, not 2858 squared, and then plus 18.93 squared. And then we see it did say that the force we wanted to the nearest pound, so whole number here, nearest whole number would be 323. So 323 pounds would be the magnitude of the resultant. Then if I want to find the direction angle, that goes back. I think that the easiest way to do that, and again, if you know another way, that's perfectly fine, is to use what I wrote out here. And it doesn't matter whether you use the sine or the cosine. In this case, I probably would just use the sine since that value for B is smaller. So B over the magnitude, so sine theta equals B value, which is 18.93, over the magnitude, which we just found to be 323. So I'm going to do inverse sine of that. And it says round to the nearest tenth of a degree. So back to my calculator. Inverse sine of 18.93 over 323. Enter. And it gives us 3.359. So to the nearest tenth, that'd be 3.4 degrees would be our resultant. All right, and we check force, magnitude to the nearest pound, direction angle to the nearest tenth. We followed all the directions, and so then we are all finished.